Okay, let's try this example. What is the Ka for a 0.80 molar solution of butanoic acid if it has a pH of 2.13? All right, so first thing we need to do is analyze what we have. We have an acid. This is not a big 6 acid. This is a weak acid. Therefore, they gave us N1 a Ka value. If ever you have a weak acid, your plan of attack, take that weak acid, put it in water with some ice, and find your Ka. So let's take this weak acid. Now, I don't really want to write down all of this formula right here. I'm going to go ahead and just use an abbreviation for a weak acid. And that abbreviation is H with all the rest, HA. I'm going to take that acid, HA. I'm going to go ahead, put it in water. My acid will weakly dissociate, give off some of its protons to make hydronium ions and the conjugate base A-. Now let's go ahead and fill out our ice table. We're going to start off with a 0.80 molar solution of this acid. So the initial value is 0.80. I don't have any substantial hydronium or conjugate base right now in my solution. These are essentially 0. So I'm going to move in the forward direction. I'm going to take away X. I'm going to add X. I'm going to go ahead and add X. At equilibrium, the A- will be X, the hydronium will be X, and our HA value is 0.80 minus X. Now we'd like to go ahead and take those values and set it equal to our Ka. The Ka here will be equal to X times X, or X squared, all over 0.80 minus X. Well, at this point, we're kind of at a standstill for a moment. We don't know Ka, and we don't know X. So there must be another number in the problem we can rely on. Let's take a look. We already used our 0.80 molar solution, but they also give us a pH of 2.13. If we have the pH, we can use that to find the hydronium concentration that we need to fill out our ice table. So let's go ahead and do that right now. I'm going to remove this to give myself a little more room. We know that we have a pH equal to 2.13. Now I can use that pH to find my hydronium if I go ahead and use the formula pH is negative log of the hydronium concentration. By fiddling around with this formula and evaluating it for H3O plus hydronium, first thing I'm going to do is take the negative over to the other side, and then I'm going to inverse log it. I can create a formula that my hydronium should be 10 to the negative whatever that pH power is. Again, I brought the negative over and took the inverse log of both sides. The hydronium in this circumstance happens to be 10 to the negative 2.13. That gives me a hydronium concentration right here of 0.0074 molar. Okay, so we've got our concentration. We can go ahead, take that, and plug that right back in for those equilibrium concentrations. The hydronium will be 0.0074 molar. The conjugate base, A-, 0.0074 molar. And if you take 0.80 minus 0.0074, you end up with a concentration of 0.79 molar. That one barely changed. All right, we're going to take those equilibrium values, put that in for my Ka now. Ka will equal X times X, 0.0074. That is going to be squared all divided by the 0.80 minus 0.0079, which is our 0.79 molar. Sorry, I think I misspoke. 0.80 minus 0.0074 gives us the 0.79 that we're going to put down here. And then if you go ahead and divide those out, you get a Ka value equal to 6.9 times 10 to the minus 5, no units, and that's fairly typical of a weak acid. I hope that helps. Take care.